Is it a function of x and z, which means that you come out the y-axis? Is it a surface this way? No. Is it a function of y and z? Yes, it actually is. Your x value, right? Your x value, you could look at this as a function of y and z. It's actually g of yz. But what is the function? 0. It's 0, isn't it? Understand? Sure? If that's how simple it is, if that's our function, then what does our formula double integral over S2, because we're only talking S2, of f of x, y, z, magnitude, well, you know what, give me the short formula, the shortcut formula. It would be square root of 1 plus partial g with respect to y plus squared plus partial g with respect to z squared, right? That's what it would be, dA. dA, yes. I need to change one thing here. We're going to call this D2, all right? Because it's the domain that draws this surface, and change this to D2. It turns out that S2 and D2 are exactly the same here because it's flat, right? What is the partial of g with respect to y? 0. What's partial of g with respect to z? 0. So that's just what? Square root of 1? Which is just 1. Double integral over d2. Now I need to plug in to my scalar function, x, y, z. What is my scalar function? X, right? I need to plug in what? 0. Right? X is 0. You understand that? This right here is just x. So I replace x with whatever x is on this surface. What is x on this surface? 0. So this becomes 0 square root of times square root of 1 dA. And what's the double integral of 0? 0. All right? Now, I'd like, since this is our first surface and our first example of using the shortcut, I'd like to show what that would have been the long way, but I'm going to go quickly through it, okay? Can I show you the long way? All right, the long way I would have had to have taken this and taken partials. What's partial of R2 with respect to U? I know that's weird notation. So 0, negative V sine U, V cosine U. What's the partial of R2 with respect to V? 0, cosine U, sine U. Cross these. Cross them. So here, what do we get? Negative V sine squared U minus V cosine squared U. I'll take care of that on the next step. Next part. What? 0, which 0, 0, so 0, and then where am I? Hold on. I did this one 0, 0. So 0 again. And what is that? Where? Oh, sine squared, yes, thank you. Factor out a negative V, right? Pythagorean. So negative V, 0, 0. And now take its magnitude. And you get what? Square root of V squared, which is absolute value of V. But v is positive, right? So I don't need to worry about the absolute value. Okay, so that's the cross product, right? And what else do I need? What? I need to evaluate my scalar function on the vector curve. It's 0, right? Because it's x. So I come in here and I plug in 0 and I'm done. Now, I could have avoided all this by noticing that x was 0 and that was the scalar function. But I just want you to see what work it would have required instead of how quick it was with that shortcut. Okay, any questions? All right, let's now go and do S2. Or that was S2. You want to do S1? Okay, let's do S1. Why is that not wanting to come back here? Okay, which one was S1? The blue one? Okay, the blue one, S1. So how would you like to handle this? You want to go, R of uv, or can you look at that as being some function of two variables? Function of two variables, right? S1 is actually just x equals 1 minus z, which again is a function of y and z, isn't it? X is determined by y and z. Now, it turns out that our function doesn't need y in it, right? Y is not in there. But x is determined by z for sure. So I've got this. I've got double integral over, let's call this d1. Okay, d1 is going to be the domain that draws me this surface. Now I plug in what? The scalar function. I replace x with, well, x is this, right? So 1 minus z. And then square root 1 plus partial of g with respect to y. 0 squared plus partial of g with respect to z. Negative 1, but then squared dA. Got it? Which is root 2. Take that out of the double integral. Root 2 double integral over d1 of 1 minus z dA. Now, this is a critical juncture we're at here. Does anyone have any questions on what I've done, though, thus far? D1 are the restrictions on my double integral that will allow me to draw that blue piece, right? 1 minus z is just the entire plane. Remember, this x equals 1 minus z is a plane, isn't it? I don't want to draw the whole plane. I only want to draw the part of the plane that's in blue. So how do I restrict my y's and my z's to draw just the blue part of that plane? Drum roll. Negative 1 to 1 on both of them would draw me a square. So look at it this way. You've got that piece right here, and I'm kind of like transposing. My x-axis comes out like this. Here's my y, right? We're taking that and we're looking at its projection down onto the yz plane. That is a polar region on the ground, isn't it? I'm going to convert this integral to a polar integral, or cylindrical, however you want to look at it. Because I can't restrict y and z to make that nice. But if I go polar, I can. So I'm going to have my theta between where and where? 0 and 2 pi. And my radius should be between 0 and 1. Right? What are the substitutions I'm going to make? This is critical that you... Because if it's a normal polar region, we go x is r cosine theta, y is r sine theta, right? This time, we don't have x, right? It's y and z. So it'll be y is r cosine theta, z is r sine theta. Yes? And look at your integral here. It just has z in it. So I'm going to make this 1 minus r sine theta r dr d theta. I'm getting nods of approval, which is why I'm continuing here. Root 2 integral, now I'm going to change it 0 to 2 pi, 0 to 1, 1 minus r sine theta r dr d theta. Remembering that when we did this over here, we are going to let y be equal to r cosine theta, let z be equal to r sine theta, because our region projected down onto the yz plane is polar, and it's in the yz plane, not in the xy plane. And then you could distribute through, right? And integrate. Do we want to take it the whole way? No? You don't want to take it the whole way? Okay. So can I dot, dot, dot this? So we get that. We're not going to be able to get a final answer then. You're just going to have to do that on your own, all right? All right, that's S1. We still have S3. Now look at S3, which kind of looks like this. Not too bad. It's not so bad, right? S3? It's pretty good. Can you write S3 as a function of two variables? No. There's just no way you can do it. You can't look at this as, anytime you can write it as a function of two variables, it's going to look like some surface that you go straight down onto a plane. It's going to be a nice shadow. Here, you can't, right? Because it wraps around itself. So you have no choice but to use the R of UV here. You've got no other option. Do you all understand? Okay, well, let's do it. I know you can do this. How are you going to draw that? I'm sorry? I didn't hear.
We did it last class.
We did something like this last class, right?
Yeah.
Or was it this exact one?
No, it wasn't this exact one. It was similar.
Okay, so look, if we look at it from this way, right, it's the green part. So it's just the edge, right? So I know I'm always going to be drawing circles in the, what plane? In the YZ plane, I'm drawing circles. It's just that the X is going to come out and go back in different places, right? So how do I draw a unit circle in the YZ plane? I've got to use these, right? So cosine, what do you want to use? U. Sine, U. That should draw me unit circle in the YZ plane. And then the V, right? The V here. And you'll control it in the inequality, right? So U is going to be between 0 and 2 pi to draw me circles. And then the V is going to be, well, what's the smallest V I can have here? V is my X value, right? So 0 all the way to the back. And then the front side, right? I want to go everywhere between here and here, right? Pick points. I'm going everywhere between here and here. And that's got to land on this plane, right? So what? 1 minus z, but z is sine u. There it is. I forgot to put v here. All right, partials cross magnitude. Set up integral. Partials. Partial of R3 with respect to u, 0, negative sine u, cosine u. Partial of R3 with respect to v, 1, 0, 0. Ooh, beautiful. And cross them. Zero, negative cosine u. Hold on, I'm not even, I'm just writing down. It's positive? Definitely, okay. We're going to square it anyway, right? When we get the magnitude. All right, what's the last one? 0? Sine u. Sine u. Oh, wow, okay. Is that going to be 1? Magnitude? Root, what? Cosine squared u plus sine squared u? Yeah, well, what? Is it negative? Are y'all changing? Okay. Okay, and that's just 1, right? Where? Root cosine squared. 1 plus. Not for magnitude. You're thinking of that shortcut thing. Yeah. No, we're just looking at the magnitude of the vectors, so square root of each of the components squared added together. All right, well, that's nice, right? That works out pretty good. So now let's set it all up. We have our double integral. We're going to be going over the region D, all right, D, which is the restrictions on u and v. We have x, right? Our scalar function is x. So I need to plug the surface equation. I need to replace the x with v, because that's the x component. So v. Then I need the magnitude of the cross product, which we know is a 1. Then dA, which is integral from 0 to 2 pi. I don't have a choice with the order here, right? 0 to 1 minus sine u of v dv du. Right? Dot, 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 or continue? Dot, 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 okay. Antiderivative 1/2 v squared, plug in, ooh. All right. Do you have the idea here? So when you're doing these surface integrals, you always want to look, can you do a shortcut? If you can, do it. If you can't, then you've got to do this. And then you would add up all those answers, yes. I didn't discuss it. I didn't put it in the notes, but if your surface, right, if you have some surface S that can be broken up into smaller pieces, right, S2, S3, if this is all S, then if you're going to do the surface integral over S, you can basically say that's equal to the surface integral over S1 plus surface integral over S2 over S3, put them all together. Even if those surfaces come around each other and close in a solid, that's fine.